Okay, let's get started. So who doesn't remember that climactic fight scene in the James Bond film GoldenEye, taking place 500 feet above the bottom of a gargantuan bowl-like structure hidden in the jungle? Some may remember the first glimpse of a massive dish seemingly carved out of forested mountains, sitting under a precarious-looking superstructure suspended by a spiderweb of steel cables being used for SETI searches in the movie Contact. What a fantastic movie set, you might have thought. But these were no movie sets. The futuristic and colossal backdrop common to both these films was the Arecibo Observatory in Puerto Rico, home to a 305-meter or 1,000-foot diameter single dish radio telescope, and for many decades, the largest and most sensitive radio telescope in the world, and certainly one of the most iconic. Hidden among the rolling forested hills of rural West Virginia, quite literally in the middle of nowhere, is another colossal structure of modern radio astronomy known as the 100-meter Green Bank Radio Telescope, the largest movable radio telescope in the world and operated by the National Radio Astronomy Observatory, or NRAO. It's a single dish larger than a soccer field, and it's mounted on a lacy-looking steel skeleton that allows it to be turned and tilted to access targets of interest across nearly the entire observable sky. Not to be outdone, the Chinese built their own Arecibo-like fixed-dish radio telescope that measures an impressive half-kilometer in diameter. It's known as the FAST telescope, or the 500-meter Aperture Spherical Telescope, and it saw first light in 2016. FAST is now the largest single-dish radio telescope in the world, but is it the last of a dying breed in the field of radio astronomy? So good morning, good afternoon, or evening, ladies and gentlemen. Welcome to our October edition of our now famously virtual SETI Talks. This is the monthly lecture series produced by the SETI Institute in Mountain View, California. I'm Bill Diamond, President and CEO. We're a nonprofit research and education institution whose mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe. Like people the world over, we're presently carrying out our work from home, but our research, education, and outreach programs continue even while the lights are out at headquarters. Our SETI Talks series has been running for more than 10 years, and if you explore the series on our YouTube channel, just go to YouTube and search for SETI Institute, you'll discover hundreds of lectures, debates, and panel discussions featuring many of the world's foremost researchers, educators, explorers in space science, covering an extraordinary range of topics. Normally, these talks are delivered to a live audience in the San Francisco Bay Area, but the series has been virtual since April. This, however, is giving us the opportunity to reach a truly global audience and share our stories and our science with people the world over. So I'd like to welcome all of our special guests joining us today live on our Zoom auditorium, and also say hello to our friends and followers with us today on Facebook and YouTube and other platforms. Today's talk is coming at an earlier time than usual here in California, which means that thousands of people across the country are stopping their work to be here with us today. So we may get in some trouble for this, but we'll just have to deal with it. It also means, however, that our friends in Europe and points further east can come along without losing any sleep, including, rather importantly, one of today's guest speakers. Regular attendees know that we always love to find out where you're joining us from. So if you're on Zoom, use the chat function that you'll see at the bottom of your screen to give us your coordinates. Tell us where you're watching from, or use the comments section on Facebook to do the same. Special kudos today for people joining us from Canada, from the United Kingdom, South Africa, and Australia. So clue us in and let's find out how far our SETI Talks beacon is reaching. We also like to poll the audience to find out who's joining us for the first time and who's a habitual fan. If you're with us on Zoom, you'll see a pop-up on your screen that will appear, and you can answer the question in the way that is appropriate based on whether you're with us for the first time virtually, or if you've been a regular attendee to these events, or even visited us in the in-person events. So we'll show the results of that in just a moment. Today, we're exploring the fascinating topic of radio astronomy, near and dear to our hearts at the SETI Institute as the primary observational technology used in the search for extraterrestrial intelligence. But radio astronomy is a critically important tool as well for understanding the structure of the universe and the history of our cosmos. We're delighted to welcome two extraordinary young radio astronomers to our program today who will discuss both the state of the art and the future of radio astronomy and the modern trend towards building truly massive radio telescopes out of many smaller dishes called radio telescope arrays, not least including the Allen Telescope Array you can see behind me, or ATA of the SETI Institute. Our tour guide for today's discussion is our own Dr. Simon Steele, an astronomer and director of our Education, Outreach, and Communications here at the SETI Institute. We will have time for your audience questions after the moderated discussion, but note that we're not able to answer all your questions, and also note that you won't necessarily see the questions in your own chat, but we do see them all, trust us, and my colleagues Rebecca McDonald and Franck Marchise will be fielding your questions on Zoom, posted via the Q&A function you can see at the bottom of your screen. So for questions, use that Q&A function on the bottom right of your Zoom screen. We may not have time for all your questions, but we'll be on the lookout for the best questions, so let the games begin. As a reminder, the SETI Institute is a nonprofit research, education, and outreach organization. It's supported in part by donations from the public, from people like you. So we invite you to join our quest and become part of our community. You can visit our website at www.seti.org for more information on how to get involved, how to help us out, or even to get on our mailing list so you can receive our regular monthly e-newsletter called Journey, which is, as the name describes, a wonderful journey into the science of the Institute. So get your safety harness on and come along with us to explore the science and engineering of radio astronomy. I'll now turn the proceedings over to Simon, who will introduce our speakers and get us started. Simon?
Yeah, thanks, Bill. Good evening, good morning, everybody. I'm looking down the list of where people are watching from. We've got Mountain View, California, which is great, Arizona, Italy, Germany, Netherlands, a huge range of places. So welcome, everybody. And as Bill said, you know, we have these magnificent giant telescopes, Arecibo, I have a picture behind me, China's FAST telescope, the Lovell telescope in the UK, the Parkes telescope in Australia. But now the next generation of telescopes like MeerKAT, the precursor to the Square Kilometre Array, and the SETI Institute's own ATA, are smaller dishes, lots of them. Covering great surface areas of the Earth. And the question is, are the big radio dishes dinosaurs? And to help discuss that and the current and future state of radio astronomy, I'm going to introduce our two speakers tonight. We'll start with Cherry Eng. Welcome, Cherry. Cherry is a postdoctoral researcher at the Dunlap Institute for Astronomy and Astrophysics. During her PhD study, she's discovered 60 rapidly spinning neutron stars with the Parkes radio telescope in Australia, nice big dish. Her hunting effort continues now with the Canadian CHIME telescope. Together with the team, she uses CHIME to detect and study fast radio bursts, and I'm sure we'll be talking about those. A new astrophysical mystery, the FRBs, that involves short radio bursts that have come from far outside our Milky Way galaxy. So welcome, Cherry. Evan Keane is an award-winning astrophysicist working in the area of time domain radio astronomy. Time variable astrophysical signals arrive from extreme physical environments impossible to create in an earthbound laboratory, and so they offer unique insights into the laws of nature. His work involves searching for pulsars and fast radio bursts and use these tools to understand the universe. Recently, he's begun working on SETI search systems, and since 2015, he's been project scientist for the Square Kilometre Array, which commences construction in 2021. Evan's role has been to ensure that the telescope designs can deliver scientifically in the time domain science, and I'm sure we'll hear what that means. So welcome, Cherry, welcome, Evan, and I'm going to turn the platform over to you now to introduce radio astronomy and your research. So I think, Evan, you're going to take it away first.
Thanks, Simon. You can hear me okay? Yeah.
Perfect.
Okay, it's great to be here. And it's great to be talking to people from such varied corners of the world. I can't possibly read the chat, but I saw lots of diverse place names going through. So I'm going to start off by trying to explain radio astronomy very quickly. So I recently been packing some stuff or tidying up my house a little bit, and I found a radio telescope, which you may also have a radio telescope like this in your house. With this, I think I can explain to you how radio astronomy works. So if you have something in the sky emitting some radio light towards your telescope, I've depicted the light as various waves of different frequencies. When when that hits the metal, it causes some charged particles to move. It doesn't cause this isn't a very large effect, but if you were to connect a voltmeter and measure the voltage in this wire, you would find that the voltage maps directly to the electric field of the light incident on the wire. And this is how we see radio waves. So you can't see radio waves with your eyes. We see voltages, and it just so happens that the voltages match the intensity of the light exactly. The problem is that this is this is a radio telescope system. Problem is this isn't a fantastic radio telescope system. So what we do is we employ big dishes, otherwise known as light buckets, to collect as much light as possible. So this is the Lovell telescope, which is about an hour south of Manchester in England. I saw somebody mention that their coordinates were 53 degrees north and 2 degrees west, which is very close to this, very close to where I am now. And so what we do is we stick our little antenna there, and we use the big dish to collect loads and loads of light and put it onto our antenna. And that is a much better radio telescope. Now, and that is essentially it. So we do other fancy things, like we cool down the wire at the focus. We actually have two wires that are sort of, across to each other to get two polarizations of light. But conceptually, that is it. And so now I'll rejig my diagram of how a radio telescope works to add in the dish. And when you do that, you collect data. You collect a lot of data. And so this is, I guess, this is sort of the technical engineering side to it. The science then is trying to search that data. You need to do a bit of there's one more thing you need to do, which is a bit of detective work. And so usually radio astronomers are very engaged in computing, and the algorithms needed to get very weak signals, weak distance signals out of these voltages, out of the radio data. So that's one way to do it. That's the big dish way to do it. You could do something else though. Even though your coat hanger antenna is not very good, it's very cheap. It works and it's very cheap. So you could just get lots and lots and lots of them. I've just done 12 there, but you could get 12,000 or 12 million of those, and it wouldn't cost as much as building some of these gigantic dishes. And if you could network them together to reproduce some of the same features you get with a big dish, but actually with some more benefits. This is an example of a real continental scale array. So this is the array solution. This is LOFAR, the low frequency array, which operates all across Europe. Each dot on that map corresponds to a lot of they're dipole antennas. So they're somewhat like those coat hanger antennas in sophistication. They're not dishes, but there's just a lot of them networked across Europe. And for many applications, you can have a European-sized telescope. Okay, I'll pass over to Cherry for this.
Can you hear me all right? Cool. All right, thanks, Evan. Yeah, so here you can see a gallery of some of the most notable single-dish radio telescopes around the world. Now, I've personally worked with some of these telescopes, including the Parkes Radio Telescope in Australia, the Evelsberg Radio Telescope in Germany. Now, Evan, if you click again, in this infograph, we can see a comparison of the size of some of these single dish telescopes. For a while, the trend has been to build bigger and bigger dishes as you can. And obviously, the advantage is that when you have a big single dish, you can collect more radio waves and so being more sensitive to the weakest signal. However, there are some downsides to this, having a big dish. You can see written here, 100-meter dishes is in fact the largest possible size of a radio telescope to be steerable. So anything bigger than that, such as the Arecibo telescope or FAST, we can't actually point them to anywhere we like. Another problem with having a big dish is the small field of view. A big telescope means a small field of view. And now, Evan, if you click again in this upcoming animation, you can see a green circle that represents the field of view of the Parkes radio telescope, which is really sensitive, but only to a small patch of the sky. Now, if you are looking for transient signals that are taking place at a known time and a known sky location, if your radio telescope happens to be looking at a different part of the sky, then you will just miss it like that. Right. And so that brings me to a new wave of SETI search that employs small interferometric radio antennas instead of single dishes. Now, the idea is that small interferometric dishes, as you can see from some of these photos here, they are smaller, which means the field of view is actually bigger. Now, if we are able to combine radio waves collected from all the available antennas together, then we'll be able to compensate and maximize our sensitivity. At the same time, we are developing new software to enable Commensal observations. Now, what I meant by that is that while other astronomers might be using these telescopes to study their target of interest, now we want to form these commensal beams that will be, and there will be multiple of them to look at nearby stars, all within the same field of view, represented by the green circle here. Now, this is a great win-win situation and a super way to use telescope resources, because we will be able to conduct SETI search 24/7, all while other people conducting other astronomy experiments. I have recently joined the Breakthrough Listen team as a project scientist for the MeerKAT and the Very Large Array VLA telescope projects. And I know that there's a similar initiative on the Allen Telescope Array, the ATA. Now, with these three facilities together, we target to survey over 1 million stars within the next few years. So that's going to be a really great boost for SETI search. Pass that back to Evan.
Okay, thank you, Cherry. So just on the topic of arrays, I've been working for the last few years on working on the Square Kilometre Array. It's actually 2 telescopes, which I have depicted here on Google Maps. So they're both arrays. One of them is in the south of Africa. So I'm just zooming in on those. In this case, each green pin represents a dish, a small dish, 15 meters in size, in this nice spiral pattern. There's reasons for that. That's in a remote location in South Africa in the Karoo Desert. The other component of the SKA is in Western Australia, which is, I have little orange pins here. In each case here, the orange pin represents 256 antennas. So not dishes. I'll show you what they look like in a second. They're also kind of in a spiral pattern. You'll see that they're not in a perfect spiral pattern, but that's because of rivers and mountains and things like that, real world constraints. So in Western Australia, we have that many of those antennas on the left. So quite a large amount of those. They're a bit taller than me in height. We call them Christmas tree antennas, which is for fairly obvious reasons. And I have a picture there with some gloves from a colleague of mine. On the right here, we have what the dishes look like in South Africa. So this is a video of this the second prototype dish being lifted into place in South Africa. So there's just under 200 of these in South Africa. So these 2 arrays sort of work complementary to each other. The South African ones work above 350 megahertz. The Australian ones work below that frequency. And that's what the SKA is. And I think that's where I'm going to leave our slides as a prelude to our discussion. Shall I stop sharing that, Simon?
Sure, yes, yeah. let's stop sharing. We can always go back to the slides if there are questions from people. So we're just going to have a little chat, and then in a short while we'll open up the questions to the audience. So please do send in your questions in the Q&A section, and Rebecca and Frog are hastily sorting through the best ones to pass on. And we've no idea what's going to be asked, so that's when it starts getting interesting. But just to start, why, and this is for both of you, maybe Cherry can start, why radio astronomy? What took you down that far end of the electromagnetic spectrum in terms of your interest? Did you just fall there, or is this something that's always intrigued you, Cherry?
Yeah, good question. So I knew that I wanted to study astronomy, and in fact, I did my undergrad in the UK, in London, where it rained a lot. And I was doing this optical project looking for an exoplanet. And I was all very excited to carry it out, but I was frustrated by the weather. It was often raining, and which meant no observations, or cloudy, and that meant no observations. So, and then I talked to my professor, and you know what? Radio astronomy doesn't care about weather. We can observe throughout the day, throughout the night, when it rains, when it snows. So that's how I got started.
Cool. What about you, Evan? Also from a part of the world, having done my doctorate in Ireland, we know about the weather, and it's not a great place to observe.
Yeah, I mean, I hadn't thought about the weather's impact on my decision, even in an indirect way. I did my undergraduate studies in the west of Ireland, which so I currently live in Manchester. People here always complain about the rain, but it's not very rainy here in comparison to the Atlantic coast of Ireland. So I knew I wanted to do astrophysics, and I did a lot of optical astronomy, but it was using space telescopes data, and did some gamma ray astronomy. But then when I started, I was doing gamma ray astronomy, and I started studying pulsars, and I noticed how precisely you could do things. I think that's what hooked me. And it's not much of a leap to realize, well, if you want to do pulsars, radio gives you much broader abilities to do that. I think I just liked the amazingly precise measurements about the universe you could make in the radio.
Wow, yes. Talking of pulsars, of course, radio astronomy has had more than its fair share of discoveries. We've got pulsars came out of radio astronomy, quasars came out of radio astronomy initially, and now we've got fast radio bursts. Cherry, can you say a little bit more about FRBs and also about CHIME, which of course is a telescope completely different from the ones we've been talking about so far?
Yeah, sure. So fast radio bursts is sort of a new phenomena in radio astronomy. These are really bright radio waves that is seemingly coming from extragalactic distances. We don't know much about them. We know more about them nowadays, but still a lot of mystery. We know that they last only for a short fraction of a second, and that's why we call them fast radio bursts. Yeah, the first fast radio burst was reported in 2007, and now it has been just over a decade. We are discovering more and more about these fast radio bursts. In the first 10 years, the progress has been somewhat slow because of the small number of fast radio bursts detected. However, as you mentioned, CHIME, this new radio telescope in Canada, has been a real game changer in the study of fast radio bursts. CHIME came online 1-2 years ago, and we have detected hundreds of fast radio bursts by now, which really helped in figuring out what these bursts are. Might be. And of course, this we always hope that these are going to be signals from intelligent civilizations, and that's sort of what pulsars started off. They had the first pulsar, which was discovered in Cambridge, England, was LGM1. I think it was classified as little green men, and then it turned out to be a physical phenomena. Evan, can you say a little bit about the physics, or what we think of the physics of FRBs?
Yeah, sure. I'd also like to say, I think Cherry's underplayed her role there and the role of CHIME recently. She mentioned the first FRB was found in 2007, and that data was recorded in 2001. So it took 6 years to record it, to figure out it was in the data. And then it took me about 3 or 4 years to find the second one, and Cherry's probably found like 3 or 4 today with CHIME. So it's really like totally different worlds now. So so in a sense we don't know that much, but in another sense we know so much more than we did a few years ago. But yeah, the physics of FRBs. So we know they last. They tend to last a millisecond, something like a millisecond. Some of them are much shorter. So you can tell a lot from that, actually, if you're brave. So there is a speed limit in the universe called speed of light, which is 300 kilometers per millisecond. That's kind of how astronomers think about these things. And that's not like it's not like a speed limit on motorways along motorways you might drive on. You can't break this, but you can also tell that any signal that lasted a millisecond, the thing that emitted it, it must be 300 kilometers in size at most. It would be physically impossible to be bigger. So just from detecting one, actually, that lasts a millisecond, the thing that emitted that was 300 kilometers in size or smaller. And that immediately tells you, all right, it's not a star, it's not a normal star, it's not a planet that's tiny. It has to be something very small. And it immediately narrows down the possibilities to 2 things, which are neutron stars and black holes. As we found more and more, we found shorter timescale things that really brought us down to a few kilometers. So these things are really tiny, the sources of these. So we see many other features like polarization in the signals and due to their brightness, we know that there's magnetic fields involved. And all of this is what we might call hair. Black holes don't have any hair, neutron stars do. So we know the physics we know is that they're coming from neutron stars. Going down into the nitty-gritty of the emission physics underneath that, I don't know, and nobody knows.
And most of these FRBs are thought to be extragalactic, or have there been any discoveries in our galaxy? Because our galaxy has neutron stars as well. What's the current state of affairs, Cherry, on this?
In fact, yeah, just very recently, CHIME and another telescope in the US, the STERA project, has detected so let's say our FRB analysis pipeline has detected a burst from a galactic source, and it turns out to be a MeerKAT. So yeah, it has created a lot of speculation that FRBs might be, or FRBs might be from MeerKATs. However, we still can't quite be so sure yet, I suppose. Finding one doesn't mean or coming from the same ways.
Okay, and MeerKATs are highly magnetized neutron stars, aren't they? So it's the same family. It seems that there are these little things are creating a whole different range of effects. And one thing you see in astronomy is that what you think are completely different objects when they're first discovered, suddenly there's a meshing of these properties into particular objects, and that may be happening here. That's really cool. I'd like to point out, just to say, we've got a lot of people listening in, Seattle, Finland. I'm looking through, somebody's from California on planet Earth. They specify that, it's good to know. It might be another California somewhere else. Petaluma, Columbus, Ohio, Boulder, Florida, Chicago, a lot of places. So welcome everybody. I want to ask a little bit more about the structure or the potential structure for the Square Kilometre Array. Now, antennae combining telescopes over large surface areas is not new. That's been going on since the sort of 60s or 70s, hasn't it? But what's new about the Square Kilometre Array? And tell us about the spiral shape. You mentioned there's spiral shape. So what's special about that?
Oh yeah. Okay. So the when you have, let's say you have two dishes that you want to use in combination, if they're quite far separated, let's say they're 100 kilometers apart, you get the resolution of of a telescope that's 100 kilometers in size. So you really see a pinpointed part of the sky, but you don't see the broad structure. So if you want to see the broad structure, you might use 2 telescopes that are 1 kilometer apart. But then you quickly say, well, I want to see all of it, you know, all the detail on every scale. So you need to fill in all the gaps. So if you maybe I can show that again, but if I can find my slides, I'm not finding it. You find that you get all these different, you get every sort of combination of distance between the dishes possible. Let me just share that again and show this picture. Right, like this. And they're sort of logarithmically spaced to fill in all the different, so you can see all the resolutions all the way. You get the big picture, so the field of view of a 15-meter dish, so a few degrees, and you get all the way in to sort of the really precise detail that you get from combining the ones in the core to the ones on the far arms, like this. Yeah, there's a lot of work going into like the optimal. There's a lot of work gone into the optimal way to configure these. Yeah, and I think I showed you the sort of real world constraints there on the Australian site. So what is different about the SKA? I guess I'll leave this up. A few things. So if you want to design the best radio telescope ever, of course you want to build the biggest one ever. But if you're not building a big dish, you want to build as many elements as possible to get as much surface area as possible. And so we call this SKA low in Australia because it's observing the lower frequencies. The sensitivity of that is just more than order of magnitude greater than anything else on the planet. The frequency range and resolution is better than anything that's there. Cherry mentioned, I'm going to use one of Cherry's images here. She mentioned that you could fill out this. So this green circle represents the field of view of a small dish, and you sort of electronically make little pixels in it to tile it out. SKA can do 1,500 of those with the South African one, or 500 with the Australian version, because the pixels are bigger at those frequencies. And this is sort of unprecedented stuff. And yeah, so these are reasons that it's different in so many different ways. All of it leads into a lot of computing power required. So you can make arrays that are sort of the size of the planet connected, but you very quickly realize the data rates are sort of like almost impossible. I mean, the raw data rate of the SKA at both sites is more than the global internet traffic. Yeah. So we can't actually grab all of the data. We have to do tricks to sort of like reduce it. But a unique leading aspect of the SKA is essentially the supercomputing that's on the back end of it as well.
Yeah, we'll come back to how much data is flowing around and how you deal with this, maybe with the next question. But Cherry, while that slide was up, I just wanted to ask about this Commensal observing program. What is happening here? You know, tell us, for people who are not familiar with what a beam is on a radio telescope, what is Commensal observing? How do you do that? How do you suck off the data? And how is this important in SETI research, which is something that you have an interest in at the moment?
Right. So as we mentioned, these smaller dishes see a bigger part of the sky. Now, by using software, we can electronically sort of divert the sensitivity of the telescope to smaller regions of the view. So then we can we could so to say make a copy of the input radio waves from the telescope, and then we can create different correlations in order to study different stars at the same time. And now this is a really well, a breakthrough literally in radio astronomy, because for a long time radio astronomy, the progress has been limited by telescope resources. Now in the past we could only study one star at a time, and now there are all these great ideas to study, pulsars, galaxy, all sorts of things, but everybody only gets a little bit of telescope time. Now with Commensal observations, we can do all these things, all these great projects all at the same time. Like I said, it's going to be a really great progress for SETI search, because we'll be able to take data and looking for technical signature all the time.
And just to follow up on this, I like this graphic. So in this case, it's showing a dish. So MeerKAT dishes in South Africa, so part of SKA Mid. And the dish sort of sees in that direction. But if you look at the Christmas tree or the coat hanger type antennas, they see the whole sky at once at the same time. So you don't even and you don't point them, you don't move them, you point them electronically. So you can look over there and over there at the same time, which is with no delay. You don't have to, you don't have to move it or anything. So that's kind of cool.
Yeah, like we saw in the other animations, you might be looking at one place, but there's something else going on in another spot of the sky, right? So we want to see all of those.
That's great. So in fact, as somebody is observing magnetars or pulsars or radio galaxies, it's almost like you're peeking over their shoulder and taking notes of what's happening in different parts of that observation. So you can do SETI research and not interrupt the other research that's going on with the telescope. So that is quite revolutionary.
Yeah, and it applies for other projects too. Other scientists might want to use this commensal capability to look at multiple pulsars at the same time, for example.
Mm-hmm. That's right. So this is for the SKA, we've built this telescope that's sort of the world leading in many ways, and we asked the scientific community, what do you want to do with it? And so we got lots and lots of ideas. We wrote a book about it, and the book weighs 9 kilos. And if you add up the time that everyone wants to use it, it's sort of like, we want to do this 20 years of work in 5 years because the demand is so high. So the telescope or some of the stuff I've been involved in the last few years is ensuring you can do these things commensally, like is illustrated here. So if you want to do a SETI search, you want to observe a pulsar, and you want to observe that galaxy, and you want to do observe some molecular lines, you can do all these at the same time, and then you can get sort of 4 years per year of observing time. And that's sort of a resource that's not being, you're sort of by adding computing resources, you're creating more time, which is something that radio astronomers always need.
Just to follow on from that, you mentioned this is a big data project, like the Large Hadron Collider at CERN. This is a ton of data coming through. Say a little bit about how that's sorted and how that's sifted through. Gone are the days of the astronomer looking at the photographic plate they've just developed. What's happening now? Tell us a little bit about the computing power and what you're pulling into this.
Yeah, okay, I can do that. So let me just, I want to show this antenna. So this antenna on the left, this observes in between 50 megahertz and 350 megahertz. So it observes a 300 megahertz bandwidth. And if you want to record the data from that, there's a mathematical theorem that says you have to do twice the bandwidth. So you have to sample this at 600 megahertz. So you need to record 600 million numbers a second. Times 2, because you have 2 polarizations. Times 256, because you have 256 of these, making 1 orange dot on my map, and you have 512 of those. And anyways, it's several petabytes a second you get to for this. So it's yeah, it's a lot. So I don't know if that's the kind of numbers you want to know about.
I did look up, if you had a petabyte of music on your iPod, it would take 2,000 years to play all the songs. So I mean, trying to put these big data quantities into relevant terms is almost impossible. So this is a huge amount and quite a big sort of computing process. Cherry, is this the same? You know, what do the computers look like? Do you have? Is it like a science fiction movie? We've got banks of computers. What are you using?
Yeah, so I guess I'm more familiar with the setup in CHIME, this Canadian radio telescope, and we don't have quite so high a data rate. Our rate is roughly the size of the cell phone network in North America, which is still quite a fair bit. Yeah, and indeed we have a huge computing cluster directly at the telescope. We have to deal with this data as soon as possible, like right where we collect it. And so this computer cluster is there, and we have this 1,000 core of graphics processing units, GPUs. Some of you might know about it. That is really high performance computing cluster that it's ingesting this high input data rate. And like you said, yeah, there's a lot of challenge because, well, traditionally for radio astronomy, you might take an observation, look at a star or something, and you might record the data to disk, save it, and analyze it later. Think about what you're going to do with that. However, with such a high data rate, we just can't afford to save any of those. So we need to come up with an analysis algorithm that is searching for, say, fast radio bursts, pulsars, or technosignature on the fly. So we need to be really careful with our algorithm now if we didn't set it up right. So we might have just lost a signal like that. And we'd have thought that there is nothing interesting and thrown away the observation.
That's actually, I just remembered, so Cherry works with Vicky Caspi, and I think she said something, I think it was her that said a good description of it. It was like trying to like take a sip of water from a fire hose in your face. That's how it is trying to like deal with the data, because it's coming at you so fast, and you need to apply so many computing operations on it to figure out if there's anything in it. Yeah, it's quite, yeah, radio astronomers are becoming sort of big data scientists, I guess.
Yeah. Just going to ask one more brief question, and then we're going to turn it over to Rebecca and Frank and your questions that have been coming in. Evan, the Square Kilometre Array, this is a big international project, isn't it? It's Southern Hemisphere, but there are lots of countries involved. How easy is it to coordinate these international efforts? Because it is big science.
Yeah, it's not easy, but I think it's definitely worth it. So they're in the, I should say, they're both in the Southern Hemisphere in South Africa and Australia. There's some reasons for that. The galactic plane is in the Southern Hemisphere, so it's great if you want to observe the galaxy. It's a great spot. They're the best radio quiet places in the world, and the ionosphere is in a good condition over these sites. Yeah, there's a lot of countries from, yeah, so I would try and name them all, but I'll probably forget one, but from all over the world involved in this. We've come up with a structure which is what we call an intergovernmental organization, which is the kind of same structure that ESO or CERN or very big projects like this operate in. And that has taken, so as well as the technical, I've sort of been working on the technical and scientific aspect of the design. There's been a parallel effort on a sort of political level to get all these countries and the science ministers of all of these countries to work together. But that has been successful, and now this organization is going forward. But it means that the project is it's got this stability for long-term stability. So it's, it takes a few years to set up, but it's like the dishes and these antennas that we're building they're physically robust for like 50 years. Like the Lovell telescope I showed in my first example of a light bucket was built in 1957, still works. It was built out of a leftover piece of a World War II battleship. Like these are radio telescopes don't fall, they don't usually like break. Although there has been
some of them fall down, but most of them are.
Yeah, we won't talk about that. But like they're quite robust. And what will be changing, of course, is every few years we'll be changing all this computing on the back, because computing abilities are growing. And in that sense, even if we don't add any more dishes or antennas, the telescope's getting better, because we can actually handle more of those petabytes a second. Because everything we're doing now it's tantamount to sort of ignoring some of the data. It was like, we'll try and get the most important bits, you know, because that's all we can do. But as computing improves, we can sort of handle all of the data. We can get to handle all the data. So adding computing as time goes by, thanks to Moore's law, we can, our telescopes are getting better without building any more telescopes.
Yeah, and it truly is a global community, isn't it? Astronomy, which is wonderful.
It really
it's
is.
a global,
it really is.
Yeah. Well, I'm going to hand over to Rebecca and Frank now, who have been compiling the best and trickiest questions from the audience. I'm kidding about that. And Rebecca, are you going to kick us off?
Hold on. Oops. I think Frank is going to ask the first
question.
question.
I'm going to ask the first questions, if you can hear me. So we have a question from Carlos Heredero, who is asking about the cost, the comparative cost between a large dish and small antennas. If you can give us some idea how much it costs for each of those projects, and if you are saving money basically by having smaller dish.
Do you want that one, Cherry?
I just know
I can answer it too.
Cost of CHIME, for example. That's roughly of the order of $20 million.
Yeah, so I can say that SKA costs a bit more than that. You can add on a zero and then go a bit higher. But I think the question about the value is there in terms of like dollars per science, for example. So I think Cherry's example of showing a little green circle on the sky, if you were to if you build an array telescope, you can see huge swathes of that sky and do a lot of different science on different resolution scales. You can't do that with a single dish. You can't just build a bigger telescope and do that. So it's not, you can't produce the same science with a single dish. So you want to see distant objects, so you need a bigger telescope, but you want to see lots of the sky at once, so you need a small telescope. So the only way to do it is to network lots of small telescopes. So I think in dollars per science, yes, much better value to build arrays.
Okay, so we've had a couple of questions about building arrays off of Earth. Is there any advantage to building arrays on the moon or on Mars, or is it even possible to have an array of CubeSats to do radio astronomy?
So yeah, there is a satellite, what's it called? Radio Astron, is it? A Russian, it's a satellite with a little radio dish on it. And that works in combination with telescopes on Earth. So that's sort of that's a satellite, it's not on the moon. But this gives you a baseline, which is, bigger than the radius of the Earth. So that really lets you pinpoint in, if you really want to zoom in on something. So that is a facility that exists. You could launch there are lots of CubeSats with detectors in various wave bands, but you might not need a big radio telescope, but you probably need one that's bigger than a CubeSat, because you need to have some sensitivity. I mean, what's the dimensions of a CubeSat? Actually, it's probably smaller than a coat hanger. But really, you have to be able to detect the thing you're seeing with each component. And if it's just too small, now you could go and put something on the moon. And I know lots of SETI people are involved in this, and I'm interested in it as well in terms of the lunar far side. And there's a big effort to make sure that this is a radio quiet area. With a view to putting telescopes there. I showed telescopes that are sort of in the middle of nowhere in deserts. CHIME is also sort of in a remote location. That's of hiding from people and all of their associated radio emissions from their phones and cars and airplanes and all this. So the far side of the moon, I guess, would be a great place to build some telescopes. It's hard to go there and do maintenance, but it would be a nice site.
And to get the data back on Earth, right?
Yeah, especially if you don't want to transmit it by radio.
Okay, thank you. So we also have a lot of questions, specific questions about the type of study that you can do in radio astronomy. And there is one question that came repeatedly, and one of them from Brian, is how you estimate the distance of an object when you observe an FRB or a pulsar? Can you describe to us how you basically derive these astronomical distances?
Right. I think, yeah, so for pulsars and fast radio bursts, we use a really clever technique called dispersion. So what it is about is that in the interstellar medium, so as the radio waves from pulsar and FRBs travel through the interstellar medium to reach us on Earth, in fact, the interstellar medium is not vacuum. It has a lot of free electrons in it. So the radio waves from pulsars, let's say, is getting dispersed as it's traveled through the interstellar medium. Now, in fact, the amount of dispersion is related to the distance of the pulsar. So the further it is, the more dispersed the signal will be. So from the amount of dispersion, we can sort of get a handle of how far this signal come from.
Yeah, and I can add to that for pulsars. So I'm just going to go back here. Oops. So I drew radio waves here as waves. So the high frequency ones would be the yellow ones. They arrive at what Cherry's describing. In reality, if this question mark was an FRB, the yellow one would arrive much before the red one, and we can kind of work out the distance from that delay. You can do that for pulsars too, but you can also do a parallax for pulsars. There's a few ways to estimate distances to pulsars. So parallax is sort of like as the Earth moves around the sun over the course of a year, the position of the pulsar will sort of shift with respect to the much more distant background stars. This is a technique used not just for pulsars. That's another way to do it.
Whoops, I lost my question. Hold on. All right, so hopefully I'll say this one correctly. Are we still hearing from FRB 180.916.J018 plus 65?
Oh, I don't know my telephone numbers well enough. Is that the repeater?
That sounds like R3, does it?
Is R3 or is it R2?
So why don't we just explain both of them just what they are, and then
you found it, right?
I know, sorry. Right. So I think this question is referring to some of these fast radio bursts, which in fact repeats. So we've noticed that for some of the FRBs, when we look at the same spot of the sky on another day, sometime later, we detect the same signal from the same location. So yeah, it was a big deal when we first found it, because most of the FRBs seem to be one-off events. So we've seen it and then never again. But the repeating ones are great because we can study them to much more detail than the one-off FRBs. So we could get a better handle on their location, whether they belong to a host galaxy and things like that. So until up to this point, I think roughly 20 FRBs seem to have been seen to repeat. So this question is about one of the 20. And I don't know about other telescopes, but CHIME is every day monitoring all these positions. So as soon as, in fact, yes, as soon as we detect something from these repeating FRBs, we put it on our online catalog that the public has access to it as well. So you can all keep track of this on our website.
Hi, thank you. So we were laughing when we saw this question, and we say we need to ask you these questions to see if you remember each FRB with all the digits. So we have question. Oh, a very interesting question from Edward Dower. He's asking if this trend could increase the possibility of a contribution of amateur astronomers or astronomers, to broaden it, so they can contribute to radio astronomy and to the search for SETI signal.
Frank, I think you broke up when asking the question. They missed the important part that said, is the trend towards small dishes and arrays something that opens up opportunities for amateur astronomers.
That's correct.
So I firmly believe that you can never have too many telescopes. So I try to I often tell people how great the SKA is, and I'm advocating for the SKA to have all the bells and whistles that it will have, but not at the expense of sort of everyone spending all their money and closing down all of the existing telescopes, because there's too much science to do, and there's science that maps very favorably to certain sizes of telescopes. So just like in the optical, I think the optical is there's a great example of small telescopes studying exoplanets from Earth. So sort of 1 meter telescopes, which are no longer sort of big, cutting edge research level, but they're perfect for exoplanets. And similarly in radio, there's a lot of science that you maybe don't need sensitivity for, you just need field of view. In which case a small dish would work. So yeah, you can't have too many telescopes, and I'm sure if anyone has a telescope of any size that's lying idle, you can contact Cherry or myself, and we'll give you ideas.
Okay, so we've talked a little bit about the differences between big dishes and arrays and what each does better than the other. But I guess one of the questions that people are asking, and it certainly is a question that we posed as we came up with how to frame this discussion, which is, will there be any more big dishes built in the future? Or are big dishes over in terms of new construction, and will we really be focusing on arrays moving forward?
I know about a few dishes. QTT is a telescope in China, which is I can't remember what its diameter is. Maybe Cherry remembers, but it's 100-meter class telescope. Because yeah, I think it is simpler conceptually, and it's simpler to build one bigger one in some senses, depending on what your science applications are. So I don't think it's the end of them, but I think the age of the array has probably taken over.
I think as we're coming up to the hour, we've got time for one question each from Rebecca and Frank.
Yeah, so we have questions. I can't find exactly where in this long list of questions we received, but there was questions about the construction of this a dish on the far side of the moon, and explaining again maybe why that's important and your thought on whether or not this is feasible in the short term.
You want me to answer that one?
You have something?
Both of you.
Okay. I mean, there's already a radio telescope on the moon, by the way, from a Chinese-Dutch mission. But the idea for there is a project called Farside, and the idea is to put radio telescope, but it's not a dish. It's more like these Christmas tree coat hanger style antennas that observe at lower frequencies, that don't require the complex assembly of a dish. It can sort of like unfold themselves, something that can be sort of robotically implemented. So yeah, it would be tricky to put up a dish. There's lots of components to a dish, but more like these other antennas.
Okay, and then our very last question, or at least from the audience, I think Simon might have a closing question. Out of all the billions of data that we've received, is there one that says, "Hello world"?
Not that I have seen yet.
Yeah, we'll keep our eyes open.
That's maybe leads into my last question, and then I'm going to hand it back to Bill for closing. And obviously, there's a lot of exciting things happening with the SKA, with the CHIME observations, and so on. I suppose looking forward, maybe, and this is quite an open question, 10, 20, 30 years. What's exciting you about the direction that radio astronomy is going. Obviously, the biggest discovery we don't know about yet because they're always, you know, out of nowhere. But what sort of things are exciting you about the accelerating pace of radio astronomy over the next 10, 20 so years? For both of you, who would like to start?
I can go first, I guess. Yeah, for me, the most exciting development is how all these technologies enabling a new window in radio astronomy, like we talked about. Yeah, so we never had such a high cadence, high resolution of data. Let's put it this way. Fast radio bursts, they were not detected before because they were so short, for example, less than a fraction of a second. So without the cutting edge technology, we just wasn't able to digitize the data at this rate to be able to detect this wave. So I think, yeah, there's a lot of exciting things that we might have never thought about that we'll be able to detect with these new technologies.
Yeah, I think it's this. I think it's the same. If you get like if you get all of the radio sources, that everything that we've ever found, and you sort of put it on a diagram of duration of the event or brightness, and you fill it all out in all this, and you put them all there, you'll notice it's mostly empty. Like there's no sources that we know about with this duration and this brightness. And the answer 99.9% of the time is because we haven't looked. And a lot of the time it's because we haven't been able to look due to the telescope or computing constraints. So, and those abilities are increasing with time. So that's the exciting thing, I think, for me.
So there's still a lot of universe out there to peer at, which is very, very exciting. Thank you so much, Cherry and Evan. Thank you, everybody, for tuning in. And I'm going to say farewell and hand things over to Bill.
Great. Well, thank you, Simon. And thank you, of course, Evan and Cherry. That was really wonderful. And I think, you know, quite an eye-opening discussion and foray into the amazing world of radio astronomy. I think your explanation, Evan, at the very beginning of the basics was terrific and a good, you know, way to provide some foundational knowledge for people because radio astronomy isn't something that people know a lot about. They've heard of it, but how it works is not so obvious. So that was really wonderful and great to have your insights from both of you and your own experiences. And of course, as Simon got into with you, you know, the amount of data that is being received and processed by these telescopes all over the world and more to come is just extraordinary. So I loved your answer, Evan, to the question about, you know, should I get my amateur radio telescope dish out there? And I think it's a resounding yes. You know, there's plenty of science to be done. So in any case, Simon talked a little bit about all the guests we've had joining us from all over the world today. And just to run down again, this is something that always warms my heart because it means that, you know, this kind of discussion, that curiosity in science and astronomy, you know, that binds us all together, no matter where we're from and no matter what corner of the planet we're from. So we had visitors today from Canada, from Chile, Argentina, Malta, Mexico, Scotland, the UK, the Netherlands, Poland, Germany, Spain, Guatemala. Tom joined us from Kenya, and Harry for the first time joined us from Finland, Bangladesh, Gibraltar, Ghana, and lots of people from India. And of course, all over the United States, California, Texas, Florida, Hawaii, Alaska, West Virginia, of course, home of the Green Bank Telescope, Washington, D.C. and Maryland area, all over New England, New York, Chicago, Colorado, Kansas, and Montana, where somebody identified themselves as another Jodie Foster. So wonderful to have so many of you from all over planet Earth joining us today for the talk. That was really great. So I want to let you know that our guests today will be receiving a mission patch. You know, these are mission patches. This isn't what they'll get, but you know, that's from the Parker Solar Probe. This is one of the patches from our own SETI expeditions that we do out in the field. So we have a mission patch for the SETI Talks series that our speakers will get, as well as the highly coveted SETI Talks mug. This is a mug. This is not the SETI Talks mug. This is just a regular mug because I'm at home and I can't show you the SETI Talks mug because they're at the office, but they will be getting one of the marvelous SETI Talks mugs that are highly coveted because they're only possessed by those who have been speakers on this series over the years. So if you have one, or if you know someone who has one, you're obviously part of a very unique community. So in any case, before we all go back to life here on Earth, let me remind you again to visit us online at SETI.org to support our outreach programs like SETI Talks, to sign up for our Journey monthly e-newsletter, or simply to learn more about our research and education programs. And a big thanks to all of you for joining us today, to our speakers, Cherry and Evan, and to Simon, Rebecca, Frank, Lee, Jasmine, and the rest of the team at the SETI Institute who make this wonderful series possible. Don't forget to visit our YouTube channel and tour the amazing array of lectures, presentations, and other videos, including a SETI talk earlier this month, which was all about the SETI Institute itself. So you'll find that there on our channel. So good day and good night to all of you. Stay safe, and thanks again for being with us today. And come back for November.